Last case is what is the normal reaction when an object is resting on a slope? Okay. Now, normal reaction, as you know, they are normal to the surface. Now,
Okay.
when the surface is slanting at the slope, that means the the normal reaction, we don't expect it to be upwards. The normal reaction, it has to be normal to the surface or in the surface of the slope. Now, in our local textbook, we call this slope an inclined plane, an inclined plane. INCLINED, inclined plane. So it's actually a slanting plane like that, a slanting surface like that. So in your textbook, it is called a slope. It's called a slope. So when this object is resting on a slope, it depends on the angle, whether the angle is very big or very small. The normal reaction here, it depends on the angle, right? Because the normal reaction is perpendicular to the surface of the slope or the surface of the inclined plane. So the bigger the angle, the more tilted will be the normal reaction, right? It is no longer vertically upwards, but it's a bit tilted. So if the angle is bigger, then the normal reaction will be tilted more. If the angle is small, it will be tilted a little bit, right? A little bit like that. So we are going to analyze the force, the mass, the force of the force, sorry. We are going to analyze the weight of the object. Okay, right. We are going to analyze the weight of the object. Let me say this is the inclined plane, right? This line here. This line here is the surface of the inclined plane. And this dot here is the weight of the object resting on the inclined plane. So this dot is resting on the inclined plane. And the weight is vertically downwards. The weight is vertically downwards. Now I'm going to resolve this red color arrow, the weight which is vertically downwards, into two components. The two components are one component, which is this one, which is along the inclined plane or along the slope.
Okay.
I'm also going to resolve it into another component, which is perpendicular to the slope, which is perpendicular to the inclined plane. So in other words, this vertical weight that is acting downward, they split it into two components. One component parallel to the slope, another perpendicular to the slope. Okay, right. So when you split the red arrow into the two blue arrows, then the red arrow no longer exists. No longer exists. It's broken down into two blue arrows. But what is the size of the two blue arrows? Okay, we start off with the the angle of the inclined plane. Let's say the angle of the inclined plane is theta. The theta, right? Theta. The angle of the inclined plane. Then I draw a right angle triangle, with the weight as one of the sides, with the weight as one of the side. So if this angle here is theta, then the angle at the top here will be 90 minus theta because I draw a right angle with the weight as one side of the right angle triangle. So if this
Okay.
is a right angle triangle, the bottom angle is theta, the top angle is 90 minus theta. So this angle here is 90 minus theta. When I split the weight into two components, so this angle here will be 90 minus theta on this side. On the left hand side, the angle will be theta. So my aim is actually to find out this angle here, this angle here. And this angle here is theta. So when I resolve the red color arrow into the perpendicular component, it will be mg cos theta. If the red color is mg, then the blue color here is mg cos theta, because it is adjacent to the angle theta. So it is mg cos theta. And how about this component that is parallel to the inclined plane? Or because it is not adjacent, it is opposite, then this component will be mg sine theta. And it is always like that. The perpendicular component is mg cos theta, and the parallel component is mg sine theta. It's always like that. So if you cannot remember the angles, this is theta, this is 90 minus theta. So finally, this angle here is theta, right? So if you cannot remember it that way, you just remember the parallel component. The component parallel to the slope is mg sine theta. The component perpendicular to the slope is mg cos theta. So you have to get this correct first, right? You have to get this correct first before we can continue with the normal reaction.
Mm-hmm.
Okay, now having resolved it into two components, I reproduce the same diagram here on the slope. I reproduce the same diagram on the slope. So now this weight is mg. It is acting vertically downwards. I split this mg into two components according to the slope. One component which is parallel to the slope is mg sine theta. Another component that is perpendicular to the slope is mg cos theta. Right? Then because now we are resting on the slope will provide a normal reaction, a normal force. And that normal force is perpendicular to the surface here, the surface of the slope. So this is the normal force that is perpendicular to the surface of the slope. Now, if we look at the diagram here, the forces here, this N and this mg cos theta, they are along the same line. They are along the same line. So therefore, I say that the normal reaction is equal to mg cos theta, right? So when we look at the component that is perpendicular to the slope, one component is n, another component is mg cos theta. So these two forces, they balance one another, right? So when they balance one another, we say that the normal reaction is equals to mg cos theta. Now, sometimes, then you may ask me, how about this mg sine theta? What is the role played by this mg sine theta, which is parallel to the slope? Okay, so I can tell you that if the slope is smooth, nothing is preventing the object from sliding down the slope. So we say that this mg sine theta is actually the net force that is causing the object to accelerate downward along the slope. So this is the accelerating force or the net force. But sometimes the slope may have friction. So the friction always opposes the motion. So the friction will be a force that is up here, moving, is up along the inclined plane, and it will balance the component that is moving downward. So there are two possible cases. One case is that this slope is actually smooth. There is no friction. So if there is no friction, then the force that is accelerating the object is purely mg sine theta, purely mg sine theta, right? But if the slope is rough, if the slope has friction, then the friction will balance the mg sine theta to prevent the object from sliding down the slope. So there are two cases. But if we just consider there's no frictional force yet, right? We consider that there's no frictional force yet, and the frictional force will come in later. So what does this case show us? So this fourth case tell us that the normal reaction is equal to mg sine theta. That's all. Normal reaction is mg sine theta. Whereas the other cases, normal reaction is mg plus mass times acceleration, mg minus mass times acceleration, and so on. So in this case, normal reaction is mg cos theta. So far, any question on this object resting on an
No.
inclined plane? No. Okay. No. We look at frictional force or the friction